Hello everyone, we are team Astra Robotics and we proudly present to you our second generation rover for the year 2026, Tara Mark II.
This year's rover features a robust 20 by 20 aluminum extrusion chassis and a bevel differential based rocker system, all while using precision laser cut aluminum and mild steel plates fused with 3D printed parts, giving us the durability and modularity while keeping the weight manageable. The drive unit features independent gate DC motors at all four wheels, giving us the required torque and stable control to navigate through challenging terrains.
The simulation shows the rocker arm under 134.8 Newton load at each wheel axle and with the pivot constraint to allow rotation. The deformation is symmetric, and with an 8 mm plate, the maximum stress was found to be around 120 megapascals, giving a factor of safety close to 2.
This year's design features a custom power delivering system. It utilizing a 3S14P battery with an auxiliary battery which provides sufficient power
of 510 watt-hour and 220 watt-hour respectively
for return to base during emergencies. All these are monitored, managed and distributed by our own custom BMS and PDB, outputting voltages 12, 24, 5 and 3.3.
A kill switch is employed to shut off power in all the systems on the rover.
For this year's drive and arm system, we have upgraded from last year's Discovery board to custom carrier boards housing STM32 nucleus.
The entire embedded stack for this year's rover has been moved over to CAN. We have a CAN bus hosting several nodes: the Jetson, STM from the arm, STM from the drive, the battery management system, voltage and current readings from the power distribution board, and miscellaneous equipment such as the GPS and the IMU. The IMU records the steer of the rover on the XYZ axis for navigation purposes and also corrects the antenna steering on the rover. We convert ROS to command velocities from the Jetson to CAN frames sent across a ROS to socket CAN bridge for the drive, and for the arm the similar way joint angles are sent. For the arm, we also utilize real-time operating systems to schedule the movement of all the joints seamlessly within the same time frame without any delay.
The navigation stack uses GPS fused stereo visual SLAM for odometry, performed in a ROS to humble environment on an onboard computing device. The rover can autonomously move in partially known environments using a custom path planning package that operates based on two assumptions. Path in known space is optimally known, and the optimal path in unknown space is a straight line to the goal. This frontier-based RRT star approach allows the rover to safely navigate in a Mars environment. Simulation and comparative results have been performed in multiple environments using Gazebo. The rover is also capable of autonomously moving towards Aruko markers while detecting objects such as bottles and mallets accurately.
The comms between base station and the rover operates at 2.4 GHz using directional antenna with our own IMU-based steering mechanism, providing a strong and reliable low latency wireless link with a tested link range of 1.2 kilometers of line of sight and 650 meters non-line of sight. The above setup enables us to transmit onboard video feeds, teleop commands, and system status to our own custom graphical user interface.
Robotic arm is controlled using a custom inverse kinematic script. Each joint is equipped with an absolute encoder that serves as a feedback to the PID controller, which independently controls each joint. The wrist is equipped with an IMU that tracks the orientation of the wrist along with homing sequence.
Building on the mechanical and electronic systems, the arm executes task-level operations including keyboard typing, switch actuation, hose manipulation, USB-C insertion, and plug engagement. Using Aruko marker detection through manipulator-mounted camera, it performs precise pose estimation for alignment and positioning. It also lifts the toolbox and places tools inside using controlled grasp and motion planning.
The chemical tests on board are Bradford tests for carbonates, hydrogen peroxide, and gram stain. These tests are detected and validated using color, edge, and effervescence detection models running on board. The onboard sensors measure physical atmospheric parameters affecting presence of life.
The IMX335 camera captures real-time images of biochemical reactions, and the Raspberry Pi processes these images using HSV and morphological filtering in order to detect the color changes and effervescence involved. The Burette test, copper ions react with peptide bonds in order to produce a violet color indicating proteins. The Bradford test, the dye binds to amino acids and shifts to blue, indicating protein concentration. These color changes are detected by the system. Hydrogen peroxide and carbonate tests detect the presence of biological activity through bubble formation and effervescence. These are detected by the system using algorithms like edge and bubble detection.
We designed this year's life science unit with a lead screw-based auger system for controlled soil collection, minimizing cross-contamination between soil layers. Peristaltic pumps are used to enable precise, isolated reagent delivery with guided tubing for secure transfer. A detachable container preserves closed cached soil samples for downstream analysis. All subsystems are mounted on dual structural extrusions for improved robustness and integration.
For this year, our overall aim was to achieve a more efficient rover that could tackle URC tasks more dynamically. Overall, we strive to achieve modular improvements as part of student research club of RV College.